Welcome everybody again. This is the sixth and the last part of the isotopic application lecture. Together we will see one of the other emerging applications like permeable reactive barrier or biosparging efficacy evaluation. Again, as I told you on the other previous lecture, we will be applying the same concept that we've been applying until now. The first one is an example of an application of a permeable reactive barrier where zero violent iron was injected into a guar gum gel. So after the application, the decrease in the concentration was difficult to evaluate based on biotic or abiotic processes. The abiotic processes were expected, but at the same time, because of this gel that was injected, the consultant and the client couldn't really understand which process was the responsible for the degradation at the site. So they decided to use the stable isotopic composition. Here you have an image. So there was the injection well, which were treating the contaminated groundwater. And if we go now to the next slide, we can see that here we have the results from the lab. So what has been done was mimicking the same zero violent reaction, but in the lab, means like in a closed system. So on the top at the right, you can see a degradation profile. So we have a production of TCE and a production of cis-TCE, and then some ethene, and then some ethane. And at the bottom you can see the stable isotopic composition for carbon and for chlorine. So let's be focused only on TCE and cis-TCE. So we can see that around like 9-12 hours of reaction, so exactly when the TCE start really degrading, so the concentration and the molar fraction goes really down, we see that the carbon stable isotopic composition of the TCE get more enriched relatively to the isotopic signature of the cis-1,2 DCE. So all the time, the isotopic signature is more enriched. After a certain time, the isotopic composition for the chlorine, again for the TC, is more enriched than the isotopic composition for the cis-TC. And it must be noted that before that point, the situation was the reverse. So the cis was enriched compared to the TC, either for the chlorine and for the carbon stable isotopic composition. So we went to the field and we collect some samples, and we ran the stable isotopic composition analysis. So you can see at the left and at the right the carbon stable isotopic composition and the chlorine stable isotopic composition before and after the barrier. So before and after we have pretty much the same distribution, where the stable isotopic composition for the cis DC is more enriched compared to the stable isotopic composition for the TC. This is valid either for the carbon and then for chlorine. So if we go to another sampling point, we could see exactly the same behavior, where the TCE is all the time more depleted compared to the isotopic composition of the cis-TC. So this qualitative parameter alone would be already enough to demonstrate that the decrease in the concentration of the contaminant was because of the biological process and not because of the reduction process expected from the iron barrier. Otherwise, we would have got exactly the same opposite trend as shown by the microcosm experiment in the lab, where the isotopic composition of the TC would have been more enriched than the isotopic composition of the cis-TC. So the red point, they should have been over the green point, as we can see again on the microcosm lab results, where the TC is more the time more enriched than the CSTC. So isotopes can also be applied in a simply qualitative way to point out main processes, like this case, for example. And another application was to try to demonstrate the main process in a biosparging experiment, trying to quantify the volatilization and the biodegradation processes. So we developed a full experiment at the pilot scale at the Borden Research Aquifer. So you can see from the picture here is the same picture that we've seen previously. This is a box, and we release 150 liters of synthetic gasoline, and we did this biospargem experiment over almost a couple of years, and we collected a whole bunch of results trying to see if the contaminant concentration alone was giving us some clue about biodegradation and sparging processes, and if the stable isotopic analysis would give the same information, basically. So as we did for the previous experiment, we went first to the lab, which means to a closed systems, and we ran several experiments to see if the volatilization itself from NAPOs and from the dissolved phase would show us some specific trends. So, for example, here we can see that the air-water partitioning, which is referring to the stripping process, we can see these results are for the benzene, that, for example, there is no enrichment on the carbon, but there is a huge enrichment on the hydrogen. So on the other side, from NAPO vaporization, which means just stripping from the NAPO or NAPO vaporization alone, we could see a depletion either in carbon and either in hydrogen. So this two behavior, the blue one indicating the air-water partitioning and the red one indicating the NAPO vaporization, we can see that they're very unique, especially if they are compared to the range of biodegradation in between aerobic and anaerobic. So theoretically, by comparing the dual isotope carbon and hydrogen results, we should be able to point out which is the main dominant process that is responsible for removing those specific contaminants. So if we look at, we collected a whole bunch of results from PID and from CO2 results to quantify, since it was a closed system, the contribution from the biodegradation and from the vaporization. Main contribute was from volatilization, but also from the biodegradation. It was quite significant. For example, at the end we got a kind of 60% from the volatilization and a kind of 30% from biodegradation processes. Now, if we look at the specific compounds results, we could see that for benzene, mostly was basically biodegraded. And if we look at the isotopic results, we can see that carbon and hydrogen get enriched, and the value they are in between this range for the aerobic and anaerobic biodegradation processes. The same for toluene, we can see here that was mainly biodegraded. And if we look at the isotopic results, again, they remain in between window for biodegradation processes, where like carbon and hydrogen are both getting enriched through the process. But if we look now more at those volatile compounds, like for example isooctane, we could see from our calculation that these compounds were mainly volatilized because they are very volatile. So I plotted here in red the trend which would be expected for NAPO, R-NAPO passive vaporization, and we can see that basically the result there are in this part of graph. So they are indicating that isoctane was mainly removed by volatilization processes. So to conclude, we have seen that stable isotopes, they've been useful for fingerprinting analysis, for biodegradation analysis, but also for monitoring the performance of new remediation technique like in situ chemical oxidation, and also applying to permeable reactive barrier remediations systems, but also for biosparging, for example. So some practical tips. The sampling is run exactly the same way as for the contaminant concentration. You just have to add the preservative, because usually labs have a long waiting list, and sometimes I think they must be very useful, although they are a little bit costly. Now, for example, usually price ranging between $200 and $450 per sample per compound. But sometimes if you consider, for example, a $4 million remediation action, that would make any. And some literature which I think have been using it for this presentation, and which I think I really recommend to you. And I really would like to thank you for your attention. I hope you enjoy a little bit this series of small lections, and again, if you have any doubt or curiosity, you can contact me at Skype, this Skype address, or at this email address at any time as you want. Thank you very much for your attention, and I hope to see you